Welcome to today's paper reading. Today's paper is titled, Tuning Language Models by Proxy. This paper was published as a conference paper at Colm 2024 by Alisa Liu and colleagues from the University of Washington and Allen Institute for AI. The abstract highlights the challenges faced with large pre-trained language models, which, despite their capabilities, require further adaptation to achieve desired behaviors. Tuning these models is resource-intensive and often impossible when the model weights are private. To address this, the authors introduce proxy-tuning, a lightweight decoding-time algorithm that operates on black box language models by accessing only their predictions, not their parameters. This method involves tuning a smaller language model and applying the difference in predictions to shift the larger model's predictions towards the desired tuning. Experimental results show that proxy tuning can close 88% of the performance gap between Llama 2-70B and its tuned version across various benchmarks. The method is also demonstrated to be effective for domain adaptation and task-specific fine-tuning. Finally, the authors show the applicability of proxy tuning to truly black box models like GPT 3.5 for temporal adaptation. The introduction of the paper highlights the increasing capabilities of large pre-trained language models, which generally benefit from additional fine-tuning to achieve desired behaviors. However, tuning these models has become increasingly resource-intensive, especially when model weights are private. To address this challenge, the authors introduce a lightweight decoding-time algorithm called proxy-tuning. This method operates on top of black box language models, using only their predictive distributions over the output vocabulary, without accessing the model's internal weights. The experimental results show that proxy tuning can closely match the performance of heavily tuned large models, such as Llama 2-70B chat, by tuning smaller models. It also demonstrates improvements in domain adaptation and task-specific fine-tuning, making it a promising approach for efficient customization of large pre-trained language models. Figure 1 illustrates the proxy tuning process, which adjusts a large pre-trained model without accessing its internal weights. This is achieved by using a small tuned model, referred to as the expert, and its untuned counterpart, the anti-expert. The difference in predicted logits between the expert and anti-expert is applied as an offset to the original logits of the base model, guiding it towards the desired tuning direction while preserving the advantages of larger-scale pre-training. The logits displayed are actual values from Llama 2-13B, Llama 2 Chat 7B, and Llama 2-7B for a given prompt from Truthful QA. Table 1 presents the responses generated by the Llama 2-13B model and its proxy instruction-tuned counterpart for specific tasks from GSM and Toxygen datasets. The Toxygen task requires the model to refrain from continuing hateful statements. The table highlights that the responses from the proxy-tuned model are significantly different from those of the base model and are entirely fluent. The annotations on the GSM response are detailed in section 6.1, with additional examples provided in Appendix E. The method described in this section focuses on tuning a pre-trained model, denoted as M, without the need to adjust its parameters. The approach assumes access to the output logits for the entire vocabulary of M. To achieve this, a small pre-trained model, M-, is directly tuned to obtain M+. The key operation in proxy tuning is the addition of a logit offset for each token, which is determined by the difference between the logits from M- and M+. This process is analogous to the concept of decoding-time experts, where M+ acts as an expert and M- as an anti-expert. The final probability distribution for the proxy-tuned model, M, is computed using a softmax function applied to the sum of the logits from M, M+, and the negative logits from M-. This method aims to bridge the performance gap between the base model M and its directly tuned counterpart, M+, without altering M's parameters. Table 2 presents the results of instruction tuning across different model sizes. The base model refers to the pre-trained Llama 2, while directly tuned refers to Llama 2 Chat. The proxy-tuned model employs Llama 2-7B Chat as the expert and Llama 2-7B as the anti-expert. The data shows that proxy tuning significantly enhances performance, closing 91.1% of the gap at 13B scale and 88.1% at 70B scale compared to the corresponding chat model. Notably, proxy tuning reduces toxicity to 0% at both 13B and 70B scales and outperforms the chat models on the Truthful QA benchmark. These findings underscore the effectiveness of proxy tuning as an alternative to directly instruction tuning large models. In this section, we evaluate the effectiveness of proxy tuning for instruction tuning using the Llama 2 model family. This family includes both base models, which are pre-trained on text, and chat models, which are further aligned for dialogue through supervised instruction tuning and reinforcement learning from human feedback. We focus on the 7B, 13B, and 70B parameter variants of these models. The evaluation is conducted on several datasets: GSM for arithmetic word problems, Alpaca Farm for open-ended instructions, Toxygen for toxicity evaluation, and Truthful QA for assessing the model's ability to handle misleading questions. We employ zero-shot prompting and greedy decoding for consistency. The results indicate that base models, particularly the 70B variant, struggle with these tasks. However, proxy tuning significantly improves performance, reducing toxicity to 0% and enhancing accuracy and win rates across the datasets. This demonstrates the potential of proxy tuning as an alternative to direct instruction tuning for large models. Table 3 presents more detailed results from the Truthful QA evaluation. It shows the percentage of informative and truthful responses for different models at 13B and 70B scales. The proxy-tuned models at both scales are slightly less informative but significantly more truthful compared to the directly tuned models. This improvement suggests that proxy tuning enhances the model's ability to preserve knowledge, which is crucial for tasks requiring high accuracy and reliability. Table 4 presents the results of code adaptation experiments. The directly tuned model refers to Codalama Python, while the proxy-tuned model employs Codalama 7B Python as the expert and Llama 2-7B as the anti-expert. The primary metric used for evaluation is pass@10, which measures the likelihood of at least one correct solution out of 10 sampled for a given problem. Table 5 presents the results of task-specific tuning, focusing on the performance improvements achieved through proxy tuning. The directly tuned models, referred to as task experts, are obtained by fine-tuning Llama 2 on either the Trivia QA or GSM datasets. The proxy-tuned model, which uses the 7B task model as the expert and Llama 2-7B as the anti-expert, demonstrates significant enhancements. On the Trivia QA dataset, proxy tuning leads to an absolute performance improvement of 19.1% over the base model. Similarly, for the GSM dataset, the improvement is 37.3%. These results indicate that proxy tuning effectively bridges the performance gap, achieving on average 84% of the performance of the true task experts. This highlights the efficacy of proxy tuning in adapting large models to specific tasks without the need for extensive retraining. Table 6 highlights the 10 tokens in Truthful QA that experienced the most significant increase in probability from the Llama 2-13B model to its proxy-tuned version. The table also provides the most common 4-gram context in which each of these tokens appears, illustrating the stylistic shifts in the model's responses. These changes include pushing back on question assumptions, addressing common myths, refraining from answering, and acknowledging issue complexity. Table 7 presents the results of proxy tuning GPT 3.5 on the real Tamika dataset. The base model of GPT 3.5 achieved an accuracy of 54.2%, which is already substantially better than random and outperforms even a small expert model. After applying proxy tuning, the accuracy improved to 56.5%, representing a 2.3% increase. This improvement is statistically significant, with a p-value of less than 0.0001. The results indicate that while the expert and anti-expert models are weaker than GPT 3.5, contrasting their predictions provides a positive signal for the base model, demonstrating weak to strong generalization. Figure 2 illustrates the percentage of responses to Truthful QA that are either informative or true, as the parameter alpha is varied in the equation Sm plus alpha, SM plus minus SM minus. The figure shows that alpha can smoothly trade off between these two metrics, indicating that users can adjust alpha based on their specific application needs. The related work section discusses several key areas. Firstly, efficient fine-tuning focuses on adapting large pre-trained models for various tasks and domains, with a trend towards scaling up model size and updating a small number of parameters. Secondly, decoding-time tuning is highlighted as an efficient fine-tuning approach, similar to DEXperts, which aims to disentangle the effects of scaling up pre-training versus instruction tuning. Our work demonstrates the empirical strength of this method. Lastly, controllable generation aims to control certain attributes of generated continuations, often through methods that operate on output logits, without requiring additional training. In conclusion, proxy tuning offers significant advantages by making large language models more accessible and adaptable to various use cases. This method encourages model-producing organizations to share output probabilities, which can further enhance the utility of these models. The research also highlights the potential trade-offs between direct tuning through updating model weights and proxy tuning through decoding time guidance. Full fine-tuning, while invasive, risks the forgetting of previously learned information, whereas proxy tuning represents a promising initial step towards more customizable, algorithmic tuning at decoding time. The authors acknowledge the valuable contributions of the UW-NLP community and express gratitude for funding from DARPA, NSF, and support from Google, Microsoft Research, and OpenAI. Thank you for watching.